Okay, I think Robert, you are online today, right?
Yeah. Alright,
Okay.
I'll start sharing. Let's see that one. You guys can still see me? Okay, cool. Da-da-da. Oh yeah, and anybody feel free to just jump in, talk over me if you know, questions, some insight if I get something wrong. Especially in the first bit. The first bit's just kind of going to be an update on to what I talked about last time. So if you missed that, I apologize.
Mhm.
Hopefully I give enough context, right? Um, okay, so let's see. I'm going to be talking about cone perception. So, why do cones matter to the GFR Club, and what's the GFR Club? Well, GFR stands for Global Formula Racing. It's a group here at Oregon State. It's also a partnership with students at DHBW in Germany, and yeah, we do autonomous vehicle racing. You can do it with a human, but humans are lame as drivers. So yeah, and so this is why perceiving cones is so important to us. You can see our whole track is outlined on one side with like blue cones, the other side with yellow cones. And you'll see some big orange cones and small orange cones in there as well. They mark different things for different race conditions. Here it's like the stop and start box.
Mm.
But let's see. This guy will finish up here pretty quick. It's pretty cool.
Yeah.
Alright.
Were you in Hossam's class by any chance?
No, I have yet to take a class by him, but yeah, he's on my
Okay, yeah.
radar.
Okay, yeah. That sounds like a very relevant thing for this.
Is he the one that does the scale as well? He does.
Yeah, 10 FR 10 or something it's called. Yeah.
Yeah, F110.
1/10.
Yeah.
1/10. Yeah. Okay. Yeah.
Yeah, that looks super interesting and right up my alley.
Mhm.
And then, so I talked about this. This was our one of our two deep neural networks we were using last time. It was Yolo V3. So this will put a bounding box around whatever you train it on. So here, this guy's been trained on a dog.
Mm.
And so here's some of the results. This was Yolo V3, what I just showed, trained on cones, and this was from about this time last year. And this was running on the actual hardware will be running on the track. So we've got the FPS up here about 30. Um, I guess I kind of included these to show where it kind of fails, the
Mhm.
old model.
Mhm.
You can see like
Mm.
this yellow one's probably the worst, right?
Mm.
The other ones look pretty okay. Um,
Mhm.
Similar, stable around 30 FPS. It's hard to tell, probably on your end as well, but this cone's missing.
Mhm.
This could be there's a part of this algorithm that's like deterministic in a sense. It's non-maximal suppression NMS, and that's
Mhm.
got a trade-off. This is one way that you might tune NMS to make it so this will predict two boxes instead of one.
Mm.
But if you tune too much towards that, you get the risk of combinations, or yeah, it's a trade-off between combining and getting separate guesses. So
Right.
it's
Here
yeah,
there are two, right? In fact, there are two here.
yeah, but it guessed them as one.
Right. Okay.
You, it never seems to be perfect. I've seen Facebook had I think it's DET or DETR. That seems interesting. They use attention to get global context to kind of solve this problem. Uh,
Mhm.
so something like that would be cool because then NMS you
Right.
never get it tuned right. It seems.
Right. Yeah.
Same thing, right? And then these guesses up here are getting kind of really wonky at this point.
Mm. Mhm.
And there's a blue stack of cones. I love this blue stack of cones. You never know if you should label this or not, and I think the model's thoroughly confused too. um, okay, so but then the problem with this old YOLO V3 model and all these results I've shown is um, we we had most of the model on the GPU, but not all of it.
Mhm.
The final there's three like final guessing layers, and none
Mhm.
of those were on the GPU. So every time that was shuffling across the bus,
Mm.
and that's not good. It's not.
Right.
It's real
Right.
slow.
Yeah.
And so yeah, so we once we got everything on the GPU, they gave us quite a big speed boost. We trained a bigger model with higher resolution.
Uh-huh.
I don't think it was actually bigger. It was just like about 2.5 times the input resolution, and we were able to get results like this, about
Wow.
double the FPS.
Mm.
Um, so that's pretty cool.
Wow. Yeah, that's good.
I've highlighted 20 meters. That's at least 20 meters. I couldn't tell. This is a German data set, and I couldn't. It's either 3 or 5 meter spacings, but either way, super
Uh-huh.
pleased with this.
Yeah, yeah.
Um, and of the like 20 test images I went through, like this is actually the one it did worst on. It's similar issues to what we were talking about with NMS. Like, see this cone? Can you see my cursor, guys?
Yeah, yeah.
Okay, cool. Yeah, this up here, if you pay
Right.
attention, it's got the same thing where it's guessing one where there should be two.
I see. Oh, what are the numbers on top you're showing?
Oh, these are like confidences, right?
Oh, okay.
Probabilities.
Okay.
So
So that should be 94.7% confidence that it is a cone.
yeah, and it's really it's nice to see it here when you got ones really up close, right? Like 99%. And then if
Okay.
once you go way out here, about that 20-meter mark, it's about 50% confident.
Uh, I
Um,
see.
yeah, and then the other place it messes up on, there's a little cheeky yellow cone peeking out
Right.
that I think I might have even missed the first time, and it misses it too.
I see.
But I'm not going to be, a begging chooser. This is a good place to be. Um, and then so like that was YOLO. So YOLO will draw this bounding box around your cone, and then we'll kind of crop to that box and feed it to RecNet, and you can see it up here. It is also just convolutional layers, residual connections. It's a lot simpler though, a lot faster. And we were able to regress this output here is like 7 channels, 2D channels, and each channel is a heat map for these key points on each cone that you've detected. So you interpret that, you get your 7 points that are most probable in the heat map, and you use the PNP algorithm, perspective in point, I think it stands for. It's used a lot in this for like essentially getting pose estimates from 2D and 3D like point pair correspondences.
Oh, I see.
So yeah, so RecNet plus YOLO got us kind of our track, right? If you detect cones and get their positions in 3D space, you've got a lot of the problem solved of mapping a track. We never got RecNet running as well as like these. This is from MIT, who originally open sourced this, and they did a big hyperparameter sweep and invested quite a bit of engineering into it. And it's like me and another undergrad working on this, and we racing time was coming up, so we kind of abandoned working on this for now for something more immediately reachable, and so we went with homography. And so I've got an example of a homography here, if somebody doesn't know what it is. So the application here, I like talking about this as like image rectification. So and in the left, we know intuitively as humans that this is like a nice square. It's got nice 90-degree angles here, but the perspective of the camera is off. It doesn't show that. Like there's not equal distance over here, and over here. So with a homography, it's really hard to tell, but there's actually like red points overlaid on this to define the bounding square. You can plug this into OpenCV. It'll very quickly give you some linear equations in the form of a homography matrix, and you can apply it to your image, and it'll rectify it. It'll turn this nice square we're saying is a square into a square.
So the right-hand side one is the one output of that?
Yep.
Oh, okay.
But plus some cropping. Yeah, it'll look a little funky, and the next slide will show the uncropped, and it looks a little bizarre. But something to point out here is once you've rectified to this plane, all of I always have a hard time trying to get this point across, but like these are equidistant, each of these like grids, right? That kind of makes sense.
Yeah.
Yeah, and we'll use that here on this next slide. So we've got the normal thing on the left, and we've got a homography so that we can project the image down to the plane that is the ground plane. and that's what we got on the right. And
Mm-hmm.
so just like over here on the right, where like these are equidistant cells,
Right.
so in a sense you can measure distance with the grids on the right. And on the right here also, once we apply a homography matrix,
Uh-huh.
you can measure distance as well. You can't measure z, you can't measure height,
Mm-hmm.
but you
Mm-hmm.
can measure to the left and forward and back. So it's
I
just a
see.
linear relationship and just measuring distance in your transformed image.
Right. Uh-huh.
Um,
Uh-huh.
I was trying to remember if this was the German or U.S. Image, and then I saw these like German cars on the right that kind of gave it away.
Okay.
Um, um,
So what are these? I guess they are looking like buildings on the right hand side. The vertical, the Z thing, Z dimension.
uh,
How do I read the right hand side picture? I
oh,
guess
what's
that's what.
going on?
Yeah.
Yeah, so this is projected to the ground plane. So we got homography to the ground plane. And
Mm-hmm.
then, were you talking about these bars or something? Oops.
Yeah, yeah, those bars, yes. The
Yeah,
colored ones and the black ones.
the colored ones. Oh, like this orange here.
Yeah, yeah, yeah.
This is these guys stretched out a whole bunch. These orange
Ah,
ones are these cones over here.
okay.
And these I've overlaid just to show that these would sort of from the point from here to here
Mm,
would be the same
mm,
distance as the point from here to here,
mm,
which you couldn't say if you were trying to measure distance in the normal camera
mhm.
perspective.
Okay, so that line is spread out on the floor. It's not going up, right?
Yeah,
The distance.
you can
Okay.
think of like the Z is like essentially squashed on the right hand side.
Oh, okay.
Where
It's
we
just XY.
yeah. We just got left and right, forward and backwards. Like everybody's real short.
Okay, I see.
And so like this is all just linear systems of equations, so it's super quick. It does
Mm-hmm.
rely on the ground actually being flat, which is not always the case,
I see.
right? So that's the trade-off. Sure, it's simple, quick, dirty, reliable, human interpretable, but um,
Yeah.
it doesn't work much beyond probably like 15 meters reliably. And
Mm-hmm,
then
mm-hmm,
we're most of those like tests of how far out does this work, we're doing static. We're not
mm,
like actually going around a corner at however many kilometers an hour, and sure it's a race
mm,
car, but um,
mm-hmm,
there's still
mm-hmm,
going to be some give to the suspension. The mount's going to vibrate a little bit with the camera.
mm-hmm.
So that's what we did in the short term. Ideally we'd like something like RetNet because it's going to perform a little better, but
Mm-hmm. Mm-hmm.
just engineering time constraints.
Right, right.
And then started taking Fuxin's class in deep learning and have some friends also interested in similar things. And so
Mm-hmm.
we thought if maybe we could take YOLO and what YOLO and RecNet does
Mm-hmm.
and combine it into one model, right? That's half the number of data sets, half the documentation, half the training, right? In theory.
Mm,
And what would that look like? What are we really trying to do with both YOLO and RecNet? We're trying to do 3D object detection.
mm.
And so
I see.
I don't know whose stinky feet these are, but this was a mobile pose detector trained on shoes, and
Uh-huh.
it's mistaken my sock for shoes. But this will tell you the rotation of the shoe and
Uh-huh.
like a 3D translation vector, so where it is in 3D space relative to the camera.
I see.
I guess
Yeah.
here would be a good maybe stopping point. Anybody got any questions or remarks on what I've said so far? All right, I'll chug on. Oh,
So
and
it's
yeah,
detecting shoes on both legs. Is that what you're saying
yeah.
right
Well,
now? Okay.
it's kind of. I just thought it was kind of funny. It messed up with
Yeah.
my sock.
Yeah.
Uh, Anant might call that an adversarial attack. I don't know.
Sure.
And then I guess the other thing is, we're in this group. This is going to be a project for Fuxin's class with two other
Uh-huh.
people, and
Mm-hmm.
I have access to a lidar because we've got one on the car. But
Mm-hmm.
I like I'm going to point out in this next slide, uh,
Mhm.
if I wanted to do, I was originally thinking let's do this 3D object detection using lidar because a
Mhm.
lot of people would just use it as the ground truth anyway when they're testing other methods. So why
Right.
not
Yeah.
just use the ground truth if it's so good? But
Mhm.
it's low res, expensive, and bulky, and the expensive part is really the really bad
Mm.
part. Like if I want to do something with my friends and have it be applicable, I don't want them
Mm.
to have to go and buy like a $5,000 Waymo lidar to be able to actually use it in the real world.
Mm. Yeah. Is that expensive?
Uh, well, yeah, yeah. The
Okay.
just last year, I was like, they came out with this honeycomb lidar here on the left, and
Mhm.
and this got hyped because it's cut the prices in half, and then you start
Mm.
searching on Reddit, how much it is or whatever, and it's still 5 grand. So, and like
Okay.
5 years ago, 10 years ago, like they were 70 grand. Like
Wow.
there's
Okay.
been
I
a
see.
lot of progress, but it's not like a flip phone camera. Like
Oh, I see.
everybody's got RGB.
Right. Right. Mm.
Um, so yeah, so all that to say, we're gonna want to put a bounding box not in just a 2D image, but like we really want to capture the 3D bounding box and its
Mhm.
orientation,
Mhm.
ideally of multiple objects, multiple classes, um,
Right.
and what we're looking at. Yeah, see, yeah, 5,000 is what I paid for my car, and I had help from my parents. So like, like, what do you expect? What we're looking at now is it's called efficient pose, but I'm going to start like working up to that. It gets the efficient name from efficient net, and so uh,
Mhm.
it's like a family of convolutional neural networks. So
Mm.
this is a model from the first efficient net, or a figure from the first efficient net paper,
Mhm.
and they just empirically showed some scaling laws that are nice for
Mhm.
scaling up convolutional neural networks.
Mhm.
So you might have some base model, and then later maybe you want to make a new model for some other device that you haven't made one for, and maybe that device has more resources, more compute available. And so
Mhm.
that's the type of scaling laws they're talking about.
Mm. I see.
And you can see it here on the right. Once they figured out those laws, that's how you get like a family of efficient net CNNs. Is just
Mhm.
scaling up the base model, and you can
Mhm.
see the trade-off as you go up this curve. And this is just compute, and then
Mhm.
accuracy on
Mhm.
something. I don't know which
No, the.
data set.
Mhm.
And it was this is I don't know if everybody's heard of NAS, like neural architecture search, but that's how they found the base model for efficient
Yes.
net.
Yeah.
It,
I see.
I really like NAS. I've yet to
Yeah, I heard
dive
of
into
that.
it, but it's
Right.
this is the reinforcement style. So they have like a controller here,
Uh-huh.
and this is what you actually will gets fed the reward signal, and you'll see.
Mhm.
I'm kind of going
Mhm.
at this backwards. Let's see. Um, so it's set up like a search problem.
Mhm. Mhm.
So the controller guides the search through the search space, where your search space,
With the
you might.
architecture.
Yeah, exactly. Maybe more people are familiar with like a hyperparameter search, or you're searching for
Mhm.
like your momentum or your learning rate or whatnot. You're pruning, but
Right.
yeah, exactly. Architecture is what we're actually searching through. This one seemed pretty tame. Like you can see on the left what they actually came out with,
Mm.
and like MBConv I had to look up. It's from MobileNet V2.
Mm.
It looks like the main thing is just changing the order in which a residual block happens and where the skip
Mm.
connection is. So really,
I see.
it's this kind of struck me. I've seen a lot of these NAS style searches that just look
Mhm.
like off the wall, a little like the cell structure can be very complicated. The interconnectedness, like with skip connections and what feeds to where, can get really crazy.
Mm.
So I was surprised to see how tame this looks on the right.
Mm. Mm.
Um, but yeah, so they use reward learning to train this controller. And
Mhm.
I guess the other interesting bit here is it's not only is the reward care about accuracy of the model, but it also cares about the latency. So just like inference time. And efficient net borrowed from this MNAS net. I'm pretty sure M just stands for mobile. You can see here this original
Oh, okay.
diagram just shows they're talking about latency specifically on phones.
Uh-huh.
Um, I think that's good for this slide. Okay, and so now we're actually getting, so we just talked about efficient net, family of CNNs that get scaled up. That's the backbone here on the left.
Uh-huh.
And then what they do here to kind of make this, what we're looking at here is like efficient det. So instead of efficient net, efficient detection, efficient det. And what they do is that they continue processing in a pyramid, like up and down it's called bi-feature pyramid network, if that means anything to anybody. But I had some speaker notes up here, but I don't have them up here. But like these layers here, the deeper layers are more semantically dense, and you can continue processing and upsampling. But with you don't. I guess you lose some spatial resolution when doing that, and that's what makes these skip connections very important. And those also, just like with ResNet, right, that helps training. It biases your network in the beginning of training towards the identity function, which is, I guess, empirically nice, right? But yeah, you just do a whole bunch of processing on top of your efficient net, and then at each layer you have these subnets. And what these subnets do is you've got classnet. That one's obvious, right? What's your class probability distribution? Boxnet, so that's the old school. That's like Yolo. Boxnet is gonna tell you, it's gonna regress like two sigmoids in the image and tell you where your bounding box is.
I see.
And then rotation and translation net, that's the 3D bit. That's with efficient pose, they assume some stuff like you have a model of what you're detecting. And the translation and the rotation net produce 3D vectors that get you to the center of the object of interest and give you its rotation. Something they don't have here that'll make it more applicable that our group is going to try to add is a scaling net. Because like they'll have like a class, they use line mod data set, which is a small data set, and they've got like duckies in there in a second you'll see, like rubber duckies, and they actually use the 3D model of the rubber ducky, and it's like always the same rubber ducky. There's no variance in the size, so there's no real need for the way they originally made this to have a scaling net. They have the ground truth.
I see. So each of these nets are they trained, or are they kind of designed it so that they do the right thing, the rotation net and translation net and so on?
Yeah, it's supervised loss.
Uh-huh.
Does that answer your question?
Right. So it is trained with some kind of supervised function which is representing the loss.
Yeah, and let's see, I can skip to that bit.
Okay. Okay.
So this is one of the major cons is like this shows up in two places, that they have this ground truth assumption, like this prior that this ducky model. And you can see here, this is like really I really like this looking at the graph here. It makes a lot more sense than the math. Like you'd have the ground truth ducky here, and let's say the model, that translation and rotation net, actually put the ducky over here and rotated this way. Their loss is just like you take similar points on the model, so like you see it's eye to eye, duckbill to duckbill. You measure the L2 norm difference between those, and you take the average, and that's your loss.
Okay, that makes sense. Yeah. So you're trying to minimize the loss. How would you rotate it? How would you map it so that the loss is minimum? That's
You get like a 20 million parameter neural network, and you hope SGD works. But this is one of the things this is our first, I think maybe this will be the last thing I say, and it's also maybe the most interesting. We want to, this method is fast already. Like the smaller model is 30 FPS on my computer. And but the big limiting thing is this assumption. You got to have this rubber ducky model for everything you want to do. So like
Mm.
you can imagine
Hmm.
if you were trying to do cars, every single car you got to have an accurate model of it. It's just not tractable.
Yeah.
I want to know, can you just go, hey, you've given me labels for some, like
Mm.
these could be your ground truth labels that some human
Mm.
produces. Um, is that enough? Can I assume the model is just a cube? Can
Mm.
I take points on the outside of this cube or uniformly distributed throughout the volume and use those in a similar loss function?
Yeah. It
So
depends on the need, right? For you, probably, yeah, you don't need the detailed mapping like in the rubber duck.
It's
It's
not even
enough to,
apparent to me that it's, yeah, I'm
yeah,
really going to have to do the experiment to see, because my intuition is it
yeah,
won't make a difference. But
yeah.
yeah, I think as Professor Prasad said, it depends on the kind of application. For cones, it may not, but say in a simple house kind of environment, this kind of details matter a lot. So I think class level categorization or understanding, say just to say that this is a duck which has been rotated is easy, maybe, but saying this is a small duck with this kind of feature which has been rotated it would be much harder, and that's where this is going to be most important to have this 3D model. So if you don't need that kind of detail, it might even work without entire 3D model.
yeah, so so this is just for training like the translation and the rotation net
Hmm.
for the center of this duck, and then they like
Right.
overlay it. Would
Mm.
it not work? Like, is there some like does the geometry get you something special? Like knowing like that it's actually shaped like a duck as opposed to you just go, it's shaped like a cube. For just guessing the center point.
Yeah, I guess it depends, right? Yeah, how accurately do you want the center point to be? Um, if you just think of it as a cube, maybe it's possible that the center point is outside the duck. That would be that would be wrong.
Well, the center point has to be in the cube though.
Yeah, it should be in the cube. Yeah, like the cube here. Let's say I just took take the outer perimeter of the cube and point out, okay, the center point. In this case, maybe it's on the neck somewhere, but I can imagine easily that it may be outside the duck.
Oh, okay.
Also, when you say center, what exactly do you mean? Do you trying to estimate center of mass of the object, or?
Just
Uh,
the center of the 3D bounding box.
Oh yeah, then I think the shape matters
yeah,
fair amount, right?
well, I don't know. Yeah, if he wants only the center of the 3D bounding box, why does the shape matter?
I think yeah, for objects like the duck, which have a varied, a weird shape where it's extending in two different directions, but not right above the back part, it might be hard. But for most objects, it might be okay.
Well, I'm glad to hear, the discussion, because, yeah, I will love to bring back the results. Yeah, we can talk about it more.
Okay.
I think I'll leave it there.
Yeah, that sounds interesting.
Yeah, no,
Yeah.
we can even talk about this offline because some of my work does kind of need this, so it would be very useful to.
Oh, that's awesome you said that. I did have a slide on some of your stuff, and I was wondering the same thing. Yeah, we should definitely talk.
Yeah.
Hmm. Yeah, especially if you want to manipulate the object, you